All right, so today I would like to teach a very important article from the guy Abraham Ittai in 2006. This guy and Yair Bartol, these two guys are my favorite computer scientists and mathematicians. So this paper is the most important, is one of the most important work on the theory of metric embedding, and you will see that many papers in 2021 are inspired by such work. And let's just remind you that a partition is just a collection of some clusters that they don't have any intersection, and the sum of all of them covers your space. And P is delta bounded if diameter of that cluster is bounded by delta. And so when I say P of X, I mean a cluster containing X. This is the cluster containing X. And the final thing that you need to know before we start is that P is called eta padded if probability of the ball of center X and radius eta delta is a subset of P of X. This probability is greater than half. This is the basic definition. Of course, recently you have much more complex definition. So what is the motivation? What is the intuition behind all of these? First, when I say I mean this is the index for scale that diameter delta I is 4 to the I. Okay, so we have space X like this. This is space X, and we want to cover it by some clusters. And of course, you can construct it algorithmically, and you have a bunch of red clusters. So they have big diameters. So these have big diameters, very, very big diameters. So they cover the space, and so they cover the space. And the nodes, the vertices of your graph are inside these balls. For example, and so we can have a different kind of cluster as well, but this time has a smaller diameter. So we call them the blue clusters. The blue clusters have smaller diameter, something like this, something like this. They cover all of our points of the graph, just like the red one, but now they have much smaller diameter. And so, for example, you have vertices here, they cover. So the blue clusters and the red clusters, they cover your space differently. But the blue clusters has a lower diameter. So the blue clusters, this delta one scale, the scale of that, delta 1, the diameter is 4. For red clusters, delta 2 is 4 to the I, so it becomes 16. And the red clusters, for example, there are delta 2 bounded clusters. And our partition for the red clusters, let's say this is S1, this is S5, S4, S3, S2. So your partition P2 refers to the scale that is interesting for us, because we can cover it in many different ways. But for the scale of 2, which corresponds to diameter of delta 2 16, we have such a partition. It has a cluster S1, cluster S2, up to cluster S5. For the blue partition, you can also cover X by P1, but P1 is like this: S1, S2, S3, S4, S5, S6, S7. So S8. So S1 through S8. These are the clusters of partition 1, which corresponds to diameter 4. So you see that in this theory, scales matters. And let's jump into the embedding. So Fi of x is sigma I of Pi of x, distance between x and x, excluding the cluster containing x. So you see, P of x is the cluster containing x. And so our embedding is now defined by those Fi's. So it's like, this is like saying that F1 of x, F2 of x, Fi of x. So this refers to the scale I, scale 2, scale 1. So this is a vector. And so the distortion, I would prove that the distortion of such embedding is order of eta minus 1 log 1 over P delta. And the dimension that you need to have is of order of log n log delta. And we'll repeat it of order of log n times in order to better approximation and lower distortion. And so let's say that what happens to the f of x, the distance between any 2 points in the embedded space. So let's calculate the LP norm of this difference. As you know, by definition, I can write the LP norm like this: Fi of x minus Fi of y to the p, and all of them to the 1 over p. And this equals to I from 0 to log delta sigma I of Pi of x. Oh, by the way, sigma I is the Bernoulli. So we write it like this: sigma I is a Bernoulli 1 over 2, because it is sometimes 1, it is sometimes 0 with half probability. So this is IID, identically independent distribution. This is Bernoulli distribution, and it plays an important role. So we cannot neglect that term. So let's carry on. So we have sigma I of Pi of x, d of x and x excluding Pi of x, minus sigma I of pi of y, d of y and x, excluding pi of y to the p, and all of them to the 1 over p. This is the LP norm of the difference. And I will show you why this is less than log delta dx and y. So I want to prove this, why this is less than this. So in order to prove that, we say that two things may happen. Either they are on different clusters, so the point x is in different cluster than y. So in this case, it is easy to see that the distance between x and x, excluding pi of x, and because we are writing this several times, let's call it a. In the Frecce embedding, we call it a. So a was an abstract set, but here we define it correctly. It's x excluding pi of x. So this one is less than the distance between x and y. It is so obvious. And if they are in the same cluster, then we use the triangular inequality. So dfx of a minus d of y and a is less than d of x and y. So let's calculate the lower bound. Lower bound. In order to do that, let's take a scale I such that delta I is d of xy over 4. What do I mean? I mean, we have a space x, always write this one. We have a space and we have a point x, and the radius is eta delta I. And so it is partitioned, for example, in this way. There are some points, some vertices of the graph again. So this point is y, for example, and this point is x. So it is easy to see that with probability half, we can say that the distance between x and pi of x is greater than eta delta I because we have created that, because we have assumed that it is eta padded. I mean, the probability, recall that probability that b of x eta delta is a subset of p of x is greater than half. So we can say with probability 1 over 4, sigma I of pi, because sigma I is, remember, this is Bernoulli. So sometimes 1, sometimes 0 with probability half. And because they are independent, so 1 over 2 multiply 1 over 2, you get 1 over 4. That's why with probability 4, 1 over 4, we have sigma I of pi of x is equal to 1, and sigma I of pi of y is equal to 0. And now, just one line. Fi of x, just by definition, Fi of x minus Fi of y, just look at the definition of f, you will see that this is greater than eta delta I, and Fi y is equal to 0 because this guy is multiplied by 0, so minus 0. And this guy is of order of eta d of x and y. Remember that eta is, eta padded. So it determines the quality of the embedding. And Bartol in 96 showed that eta is 1 to the log n. Many authors work on this because it is an important parameter for the lower bound. So Rao 99 said that for planar metrics into L2, embedding planar metrics into L2, we have eta of order of 1. And so you see how eta plays an important role. So the authors thought that we can write it with something more intuitive, and that's the local growth rate. At point x and radius r. So what is that? It means that this local growth rate, denoted by rho of x and r, is the cardinality of the ball of x and the greater radius, much greater than radius, divided by the cardinality of a ball with a center x and a much smaller radius. And so all points in a cluster have the same padding parameter, and we will use that. So in the uniform partition lemma in this paper, in 2000 paper, so the lemma says that there exists a uniform probabilistic delta bounded partition such that for any x in that cluster, remember, in the same cluster we have the same eta. So this one, so we can construct such an eta where V, this center, is argmin of this local growth rate, which is center x and delta. Don't forget that this delta is, it is delta bounded. So you have a cluster C that is delta bounded. So we are now ready to embed it into one dimension. Because if you understand embedding into one dimension only, then you can understand the big picture and more advanced embeddings, which leads to lower distortion. So delta I, remember, that is our scale. For each scale, we can have a different partition. So for each scale, we create uniformly padded probabilistic delta I bounded partitions Pi. And we define our embedding, f of x is our embedding, to be the sum of fi of x. In previous embedding that I was talking, it was a vector. Now it is the sum. And you see, it is the dual of that. So you either have one coordinate, just one coordinate, but you write it as a sum, or you have a vector and you write it like this. But the authors noticed that they are dual to each other. So from now on, from 2006, let's write it as a sum of fi of x, where fi of x is the same thing. We have Bernoulli of pi of x. So this is Bernoulli, sometimes 1, sometimes 0, times eta I of x minus 1, times distance between x and x, excluding the cluster that contains x. So the